Welcome to this rigorous scientific lecture on the molecular basis of taste and flavor in cooking. Today we'll explore how physics, chemistry, mechanics, and thermodynamics govern the sensory experience we call flavor. Let's begin with the fundamental question. What are the 5 basic tastes, and what molecular structures trigger them? Sweet taste is triggered when molecules like glucose, fructose, or artificial sweeteners bind to the T1R2, T1R3 heterodimeric G-protein-coupled receptor. The binding affinity depends on the hydroxyl group configuration and molecular geometry. Salty taste is mediated by sodium ions passing through epithelial sodium channels, or ENaC, creating a depolarization cascade. The threshold is approximately 10 millimolar sodium chloride. Sour taste results from hydrogen ion concentration. Acids like citric acid or acetic acid donate protons that activate specific ion channels with detection thresholds around pH 4 to 5. Bitter taste is detected by the T2R receptor family, with humans having approximately 25 different T2R genes. This evolved as a toxin detection mechanism, responding to alkaloids like caffeine and quinine. Umami, or savory taste, is triggered by L-glutamate and ribonucleotides, binding to T1R1, T1R3 receptors. This detects protein-rich foods, with synergistic amplification from inosine monophosphate or guanosine monophosphate. Here we visualize the 5 basic taste categories. Each is detected by specialized receptor proteins on taste cells, which are themselves organized into taste buds containing 50 to 100 cells each. Let's ask a fundamental question. Why does sugar taste sweet? What is the molecular mechanism? The answer lies in molecular recognition. Sucrose, a disaccharide with molecular formula C12H22O11, has 8 hydroxyl groups that form hydrogen bonds with specific amino acid residues in the T1R2, T1R3 binding pocket. Sucrose plus receptor forms a receptor-ligand complex. The binding energy is approximately 20 to 30 kilojoules per mole, driven by multiple weak interactions. The Gibbs free energy of binding equals enthalpy change minus temperature times entropy change. At body temperature, which is 310 Kelvin, the negative delta G indicates spontaneous binding. Let's perform a back-of-the-envelope calculation. What is the dissociation constant for sucrose binding to the sweet receptor? The dissociation constant equals E to the delta G over RT, where R is the gas constant, 8.314 joules per mole Kelvin. With delta G approximately negative 25 kilojoules per mole, we get Kd approximately 10 to the minus 4 molar, or 100 micromolar. This matches the sweet detection threshold remarkably well. Now let's transition to flavor, which is distinct from taste. Flavor is predominantly determined by volatile aromatic compounds detected by olfactory receptors. Humans have approximately 400 functional olfactory receptor genes. A molecule's volatility is governed by its vapor pressure, which depends on intermolecular forces and temperature. The Clausius-Clapeyron equation quantifies this relationship. The natural log of vapor pressure equals negative delta H vaporization divided by R times 1 over T plus a constant. This tells us that heating dramatically increases volatile compound release. Consider vanillin, the primary flavor compound in vanilla. Its molecular formula is C8H8O3 with molecular weight 152 grams per mole. When we heat vanilla, the vanillin molecules gain kinetic energy. According to the Maxwell-Boltzmann distribution, more molecules exceed the activation energy for vaporization, creating the characteristic aroma. Let's calculate. The enthalpy of vaporization for vanillin is approximately 65 kilojoules per mole. At 180 degrees Celsius, or 453 Kelvin, what's the vapor pressure increase? Using the Clausius-Clapeyron equation in ratio form, P2 over P1 equals E to the delta H vaporization over R times 1 over T1 minus 1 over T2. Plugging in the numbers, 65,000 over 8.314 times 1 over 298 minus 1 over 453. This gives approximately 10 to the 5th, meaning vapor pressure increases 100,000-fold when baking. Now let's examine the Maillard reaction, perhaps the most important chemical transformation in cooking. This is a non-enzymatic browning reaction between amino acids and reducing sugars. The Maillard reaction rate is exquisitely temperature-dependent following the Arrhenius equation. This explains why searing meat at high temperature creates entirely different flavors than boiling. The rate constant K equals A times E to the negative EA over RT, where EA is the activation energy, typically 100 to 150 kilojoules per mole for Maillard reactions. Let's quantify this. How many times faster does the Maillard reaction proceed at 150 degrees Celsius compared to 100 degrees Celsius? Using the Arrhenius equation ratio, K at 423 Kelvin over K at 373 Kelvin equals E to the EA over R times 1 over 373 minus 1 over 423. With activation energy 120 kilojoules per mole, this gives approximately 35 times faster. This enormous rate increase explains why high-heat cooking produces such different flavors. The Maillard reaction is incredibly complex, producing hundreds of different flavor compounds. Pyrazines give roasted, nutty notes. Furans provide caramel flavors. Diophanies contribute meaty, savory characteristics. Many flavor compounds are lipophilic, preferentially dissolving in fats rather than water. This is quantified by the partition coefficient, symbolized as P. The partition coefficient P equals the concentration in octanol divided by the concentration in water. Octanol is used as a model for biological lipids. Consider beta-ion-1, a key flavor compound in butter with a violet-like aroma. Its log P is approximately 4.7, meaning it's 30,000 times more soluble in fat than water. Log P equals 4.7 means P equals 10 to the 4.7, approximately 50,000. This extreme lipophilicity explains why butter delivers such intense flavor. The rate at which flavor molecules diffuse from food to our taste receptors follows Fick's laws of diffusion. This is fundamental physics governing flavor perception. Fick's first law states that the flux J equals negative D times the concentration gradient dC dx, where d is the diffusion coefficient, typically 10 to the minus 9 to 10 to the minus 10 meters squared per second for small molecules in water. Here's a practical question. If you add salt to a pot of soup and don't stir, how long until you taste it at the surface? Let's calculate using Fick's second law. Fick's second law, partial C partial T equals d times partial squared C partial x squared. For a diffusion distance of 10 centimeters and d equals 10 to the minus 9 meters squared per second. The characteristic diffusion time is approximately x squared over 2d. That's 0.1 squared over 2 times 10 to the minus 9, which gives about 5,000 seconds or 1.4 hours. This is why stirring is essential. Many culinary processes involve emulsions, like mayonnaise or hollandaise sauce. These are thermodynamically unstable systems stabilized by surfactants. The free energy cost of creating an emulsion equals gamma times delta A, where gamma is the interfacial tension, typically 20 to 30 millinewtons per meter for oil-water interfaces, and delta A is the increase in interfacial area. Let's calculate the energy required to emulsify 100 milliliters of oil into droplets of 1 micrometer diameter. This is a realistic size for mayonnaise. The total surface area of spherical droplets equals 6 times volume divided by diameter, with V equals 100 milliliters or 10 to the minus 4 cubic meters, and D equals 10 to the minus 6 meters. This gives A equals 600 square meters. That's an enormous surface area equivalent to about 1.5 tennis courts, created from just a small cup of oil. With gamma equals 25 millinewtons per meter, delta G equals 15 joules. This seems small, but without emulsifiers like lecithin from egg yolk, this energy would cause rapid phase separation. Chemical reactions in cooking generally follow the Q10 rule. Reaction rates approximately double for every 10 degrees Celsius increase in temperature. Q10 is defined as the ratio of rate constants at temperature T plus 10 to temperature T. For most enzymatic and chemical reactions in food, Q10 ranges from 2 to 3. Consider cooking a steak. Traditional pan searing reaches 200 degrees Celsius, while sous vide uses 55 to 60 degrees Celsius. What's the chemical rate difference? Using Q10 equals 2, the rate ratio is 2 to the power of 200 minus 60 divided by 10, which is 2 to the 14th, approximately 16,000 times faster. This enormous rate difference explains why high-heat cooking produces Maillard, browning, and caramelization, while sous vide preserves delicate flavors and prevents overcooking through precise temperature control. Let's examine capsaicin, the molecule responsible for spicy heat in chili peppers. This is fascinating because capsaicin doesn't activate taste receptors at all. Capsaicin binds to TRPV1 receptors, which are vanilloid receptors that normally respond to temperatures above 43 degrees Celsius. This creates the sensation of burning heat. Capsaicin has an extremely low dissociation constant, approximately 10 to the minus 9 molar or 1 nanomolar, making it incredibly potent. Pure capsaicin registers 16 million Scoville heat units. When capsaicin molecules bind to TRPV1 channels, they cause calcium ion influx, generating action potentials that the brain interprets as burning pain. This is a brilliant example of molecular mimicry. Salt and sugar don't just provide taste. They dramatically affect texture and flavor release through osmotic effects governed by thermodynamics. The osmotic pressure pi equals IMRT, where I is the Van Hoff factor, M is molarity, R is the gas constant, and T is temperature. For sodium chloride, I equals 2 due to dissociation. Consider brining chicken in a 5% salt solution, which is approximately 0.85 molar. What's the osmotic pressure at room temperature? Pi equals 2 times 0.85 times 8.314 times 298, which gives approximately 4,200 kilopascals, or about 42 atmospheres. This enormous pressure drives water into the meat. Proteolytic enzymes like papain in papaya or bromelain in pineapple catalyze peptide bond hydrolysis, tenderizing meat through controlled protein degradation. Enzyme kinetics follow Michaelis-Menten. Velocity equals Vmax times substrate concentration divided by Km plus substrate concentration. For papain, Km is approximately 10 to the minus 4 molar. There's an optimal temperature around 60 degrees Celsius, where enzymatic tenderization is maximized. Above 70 degrees, the enzyme denatures and activity drops precipitously. Caramelization is the pyrolysis of sugars at temperatures above 160 degrees Celsius. This is distinct from the Maillard reaction as it doesn't require amino acids. When sucrose is heated above 170 degrees Celsius, the glycosidic bond breaks, forming glucose and fructose. These further decompose through dehydration, isomerization, and condensation reactions. Sucrose loses water molecules, forming compounds like caramelins with formula C12H22O11-X plus X water molecules. The process continues, creating the complex mixture we know as caramel. Caramelization produces diacetyl giving buttery notes, maltol providing cotton candy sweetness, and furan derivatives contributing caramel flavor. The exact profile depends critically on temperature and time. Ice cream demonstrates fascinating phase transition physics. It's a complex multi-phase system containing ice crystals, air bubbles, fat globules, and an unfrozen aqueous phase. The freezing point is depressed according to colligative properties. Sugar and salts lower the freezing point, keeping some water liquid even at minus 15 degrees Celsius. The freezing point depression delta TF equals Kf times molality, where Kf for water is 1.86 Kelvin per mole. A 28% sugar solution depresses the freezing point by approximately 3 degrees Celsius. Rapid freezing produces small ice crystals, giving smooth texture, while slow freezing produces large crystals causing graininess. This is controlled by nucleation kinetics and growth rates. Heat transfer and cooking involves all three modes: conduction, convection, and radiation. The rate determines texture and flavor development. Fourier's law of heat conduction. Heat flux Q equals negative Ka dt dx, where K is thermal conductivity. For meat, K is approximately 0.5 watts per meter Kelvin. Let's calculate. A 2 centimeter thick steak initially at 5 degrees Celsius is placed on a 200-degree pan. How long until the center reaches 55 degrees? Using the heat diffusion equation, time approximately equals L squared over 4 alpha, where alpha is thermal diffusivity, approximately 1.4 times 10 to the minus 7 meters squared per second for meat. That's 0.01 squared over 4 times 1.4 times 10 to the minus 7, giving about 180 seconds or 3 minutes. This matches cooking experience remarkably well. pH profoundly affects flavor perception and chemical stability. The Henderson-Hasselbalch equation governs acid-base equilibria in food systems. pH equals pKa plus log of conjugate base concentration over acid concentration. For acetic acid and vinegar, pKa is 4.76. Foods with high buffering capacity resist pH changes. This is why adding lemon juice to a cream sauce must be done carefully to avoid curdling, which occurs when pH drops below 4.6. Finally, let's consider how all these molecular phenomena integrate into the complete flavor experience. This involves orthogonal sensory inputs combining in the brain. True flavor is a multimodal percept. Taste receptors on the tongue, olfactory receptors in the nose, trigeminal nerve activation for sensations like cooling or burning, and mechanoreceptors for texture all contribute. These sensory modalities converge in the orbitofrontal cortex, where they are integrated into a unified flavor perception. This is why holding your nose dramatically changes flavor perception. Let me summarize this rigorous journey through flavor science. At the molecular scale, flavor arises from specific binding interactions between tastant molecules and receptor proteins, governed by thermodynamics and characterized by dissociation constants. At the microscale, diffusion processes described by Fick's laws control flavor release, while phase transitions determine texture. At the macroscale, heat transfer through conduction and convection drives reaction kinetics following Arrhenius behavior, creating flavor compounds through Maillard reactions and caramelization. At the system scale, the brain integrates taste, smell, texture, and temperature into the unified percept we call flavor. Fundamentally, cooking is applied molecular thermodynamics and kinetics. Every culinary technique is an exercise in controlling molecular transformations through precise manipulation of temperature, time, and chemical environment. The key principles are universal: binding thermodynamics for taste and smell, reaction kinetics for flavor development, heat and mass transfer for cooking, and colligative properties for texture. In conclusion, the science of flavor is a beautiful intersection of physics, chemistry, thermodynamics, and biology. Understanding these principles allows us to predict, control, and innovate in the kitchen with precision and creativity.